Welcome to qnawire.
Hi, we're going to have the following buffer solution, which is going to contain 0.30 molar of potassium dihydrogen phosphate. In this case, the ion associated to this is going to be H2PO4 minus, which is going to be our weak acid. And we're going to have 0.316 molar of hydrogen phosphate, which is going to be our conjugate base. In this case, we're going to have HPO4 2 minus. So for this scenario, the pK associated to this pair is going to be equal to 7.2, and we want to calculate what is going to be the pH after the addition of 0.0327 mole of sodium hydroxide. So that hydroxide is going to react with the weak acid as follows. We're going to have H2PO4 minus plus OH minus, which is going to produce HPO4 2 minus. And we're going to have 150 milliliters of this buffer, which is going to be equal to 0.15 liters. So, the initial amount of mole that we're going to have of the weak acid, I'm going to abbreviate it as WA of H2PO4. Remember that this one is going to be the conjugate base, would be equal to the volume in liters times the concentration in molarity that we're going to get. So, it would be 0.15 liters multiplied by 0.300 molar. To give the appropriate amount of significant figures, we need to add those zeros, and this is going to give us 0.045 mole. We're going to do the same thing with the conjugate base. In this case, the only thing that changes is going to be the concentration, which is in this case 0.316 molar instead of 0.300, which gives us 0.047 mole. So over here, what we can do is write down our ice table directly in terms of amount of mole of the solution present. So initially we're going to have of H2PO4 minus 0.045. We're going to add of OH minus 0.0327, and we're going to get of HPO42 minus 0.047. Of course, this reaction is also going to generate water, but remember that water doesn't enter the equilibrium equations since it is going to be a condensed phase whose activity is equal to 1. So the amount of change is given by the OH minus added to the solution, 0.0327 minus 0.0327 and plus 0.0327. This is going to give us that at equilibrium we're going to get 0.0123, 0, and 0.0797. All of this is going to be in amount of mole. So now we can apply directly the Henderson-Hasselbalch equation given the value for pKa that I provided over here. In the case that you have a different value of pKa given to you in a previous question, you can use that value instead. So according to Henderson-Hasselbalch equation, the pH is going to be equal to the pKa plus the logarithm of the concentration of the conjugate base, in this case HPO4 minus, divided by the concentration of the weak acid, H2PO4 minus. Since the total volume is going to be the same, what we're going to get is that we can write down this equation directly in terms of the amount of mole of the conjugate base divided by the amount of mole of the weak acid. This is because the total volume of the solution stays the same. They're going to cancel out when we do the division, so we don't need to calculate the concentrations. We can do directly the operation with the amount of mole. So the pH would be equal to 7.2 plus the logarithm of 0.0797 over 0.0123. In this case, we're going to have more of the conjugate base than we have of the weak acid, so we're going to expect that the pH is going to be higher than the value of the pKa. So in this case, the result is going to be equal to 8.0, keeping everything to two significant digits on the pH. If you want to keep three significant digits, it would be equal to 8.01. And with that, it would be all. Thank you very much and have a good one.